before we start. So, Tyagi is going to present his research. If you want to ask questions during the presentation, feel free for the committee. I would ask that the non-committee members wait till afterwards to ask their questions, but you guys feel free to ask questions at any point. After the presentation, everyone, so you guys can ask as many questions as you want, up to a limit. We'll stop you if it goes too long. And then we may ask you to leave. The committee may ask more questions privately with Tyagi, and we'll ask Tyagi to leave, we'll deliberate, and then we will announce the news. So, Zach, go ahead and present.
All right. Good afternoon, everyone. Thanks for coming. To introduce my committee members, Major Professor Dr. Reed, and Dr. Palmer, and Dr. Gaines. So the outline. So the outline which I'm going to follow for the presentation is essentially the goals and objectives, the background, the design, experimentation, findings, conclusion, and future work. So the goal of this project was to show that an asymmetric prosthesis can exhibit the kinetics and kinematics of symmetric walking. The objectives for the time period I was given the thesis was to design and build asymmetric prosthesis and do initial testing on it and analyze the kinetics and kinematics of it. And I'll get to the details of how we did it in the experiment section. So starting with the background, so human gait. Human gait is essentially the cyclic motion of putting one leg in front of the other to move forward. As you can see, it consists of 8 major phases. There's the stance phase where the leg is mostly on the ground, and it ranges from heel strike, which is initial contact, to terminal stance where you toe off. And the swing phase is when the leg is not in contact with the ground, and it ranges from toe off to heel strike, as seen from pre-swing to terminal swing. So in this research, we're concentrating on transfemoral amputees. And what is transfemoral amputation? It is the amputation above the knee. And we're also looking into knee disarticulation, which is where a person, everything below the knee is removed surgically. Essentially the patella and the tibia, to be more specific. And the width of the residual stump is more often than not larger than the actual thigh, because during surgery, the surgeon has to add extra tissue in order to brace the residual stump. 2 kinds of prosthetics are available. And today, there's the active prosthesis, which is prosthesis which has a hydraulic, pneumatic, electronic control with microprocessors embedded in it, and the genium knee is actually can simulate very symmetric gait. And Jaipur knee, which you see on the right, is a completely passive system, which is very low cost, and as you can see, it's just fixed to the hip in the person. And a lot more units of the Jaipur knee has been sold than the genium knee due to the cost difference and the ease to make it. So why is this research very important? Because in transfemoral amputees, they expend more energy in walking than when you have a symmetric body. And amputees compensate by either twisting their hip or leaning too much on the intact leg or doing all sorts of crazy asymmetric motions to actually keep stable and walk properly. And I've also looked into the background within the similarities between the gait asymmetries of transfemoral amputees and stroke victims. Stroke is essentially the condition where if you draw a line in the center of your body in this way, and you consider one side to be neurologically dysfunctional. And the research that's shown below in the picture is the gait enhancing mobile shoes, which Mr. Hanzik et al. Did it. This simulates the split bell treadmill, and a split bell treadmill is essentially a treadmill that can simulate different speeds for each leg. So they took that concept, applied it to the foot, and they can simulate that in just the shoe. And this is important because the major asymmetry with stroke victims is that their step length is in the lagging leg, which is the neurologically dysfunctional leg, is very small compared to the step length of the healthy leg. Now, prosthetic simulators have been around for a long time, which is they're easy to test as all sorts of prosthesis, and as you can see in B, which is a very recent paper on completely active system, and as you can see, the healthy leg is actually lifted by a certain amount, so that the knee is actually symmetric to the healthy leg. And in C, you can see it's essentially a stump. It doesn't have a knee. And in D, it's a pneumatic prosthetic simulator, and as you can see, the knee is shifted to the side. And this is important because this might cause asymmetric torques and variances, which were not actually shown, but in my design, this is not happening. It will be in line. So, but the very interesting case is A, where that is the transfemoral prosthetic simulator as well. And they were studying the empathy that is created with walking on prosthesis, and they wanted to show to able-bodied people. And for convenience sake, they shifted the knee downwards, but they never studied anything about asymmetric knee locations, which is essentially the research what is focused on. Because I'm studying the knee at different positions below its actual anatomical position. So the whole concept of the asymmetric prosthesis evolved from passive dynamic walkers. And before talking about passive dynamic walkers, imagine a rimless wheel. And rimless wheel is essentially, you have a spoked wheel, and then you take the rims off, and you let it roll down. Thank you. You let it roll down a slope, and the rimless wheel will do it, and because it achieves dynamic equilibrium. And this concept was taken further and applied onto a mechanical biped, a passive mechanical biped, by McGear to do the same. And he calls the passive, and that's the passive dynamic walker. That's the first version. It didn't have knees. It was just a hip mass and 2 leg masses simulated over there. And it walks down a slope just by the force of gravity. And that model was extended by Chen by adding 5 masses. It's essentially a hip mass, 2 thigh masses, and 2 shank masses to simulate the different masses in the system. And then that was successfully proven. And then the next design was a 9-mass model, which was done by Honeycutt et al. At USF. And that simulates 9 masses, which essentially adds another mass for each thigh and each shank. And they realized that, okay, so now we can adjust all these masses, so we can go ahead and adjust the masses accordingly so that we can have an asymmetric system, but which can simulate symmetric walking. And that's where the asymmetric walker by Honeycutt et al. And this is again important because how do you say that, okay, take a passive dynamic walker model, but then how do you analyze gait with human gait with it? And the study done by Hanzik et al. Shows that you can simulate symmetric and asymmetric gaits using a passive dynamic model. And this was done with the passive dynamic model that was shown in the last slide to compare with symmetric gait of humans. And they also did a study where they added extra masses to the shank and did the same modifications onto the model, and then they proved that yes, these results are comparable, and hence proves the concept. And they use the 7-mass model: is hip, thighs, and shank, and then the foot. And this proves that yes, we can use, and this is applied. This can be applied to the real world. And this is the concept, the diagram that pretty much puts it all in perspective, showing how the prosthetic knee can be shifted from its anatomical position by Sushkov et al. So the design. So well, when designing a prosthesis, there are a lot of aspects to be considered. And in my design, I specifically chose a single-axis system, so it rotates. It also has a translational component.